15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again and welcome. Thank you for joining us on episode 197 of the Space Nuts podcast, where we talk astronomy and stuff. That's the logo. That's on our logo. Astronomy and stuff. My brother thought of that caption. I think it basically sizes us up good and proper. And joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. I'm never quite sure which of us does the astronomy and which does the stuff.
I'm sure I do the stuff and do a lot of stuffing up too. So goes to the territory.
Yeah.
How are you, sir?
I'm well, thank you. Holding up, working from home, of course,
Yes,
but
me too.
that's not much different from normal. And things like this, and our ongoing series of cosmic relief webinars, all can be done from home.
Yes, it's amazing what we can do from home and how productive we can still be. And I'm so thankful for the technology that's available that enables us to do this because, 20 years ago, we would have really struggled.
Even 10 years ago, I think we'd have had a problem. Absolutely.
Yeah. A colleague of mine sent me a little article that she spotted in an historical document a few days ago. This was published on the 7th of November 1918, a public notice in a newspaper. It says, "Notice is hereby given that in order to prevent the spread of Spanish influenza, all schools, public and private, churches, theatres, movie picture halls, pool rooms and other places of amusement and lodge meetings are to be closed until further notice." Sound familiar?
Yeah.
Here we are 100 years later.
It's remarkable that it's almost exactly a century ago. Was that from an Australian newspaper?
I believe so. D.W. Sutherland, the mayor. So I'm just trying to find out.
Yeah, exactly. It probably is. That's right. Extraordinary. That was published by a local bowling club. So, so I'm not sure. The city of Kelowna. There you are. Okay.
Kelowna. So it may well have been somewhere else overseas. Might not have been Australia, but that would have been happening all over the world, just like it is again now. It's fascinating and terrifying, all at the same time. Now, Fred, let's try and put a bit of comic relief into people's lives. And talk astronomy.
Yeah, exactly. Well,
we've got a fair bit
comical.
No, it can be. We've got a few things to talk about. Last week we talked about a collaboration between Airbus and the European Space Agency. Well, today we're going to talk about another collaboration involving both of those groups, but also involving JAXA, the Japanese Space Agency, and this is all about a mission to Mercury. Something interesting is about to happen, probably just as you're listening to this podcast, unless you're real slow and waited a week. We're also going to look at the first double helium core white dwarf gravitational wave source that's been detected by astronomers, which sounds utterly confusing but very exciting all at the same time. We are going to tackle a couple of questions, one from Pat about the appearance of all these satellites in our sky. We have talked about them before, but they're worth discussing again for all the right and wrong reasons, really. And another question, this one from Peter, who's sort of reflecting on our discussion about the Roche limit and has an interesting thought about the moon getting slightly within that limit and not going all the way and crashing into Earth. What would be the effect then? That could be interesting. So we'll have a chat about all of those things on this edition of Space Nuts. But first, Fred, let's talk about this collaboration, Airbus, ESA and JAXA. They're sending a probe to Mercury. Now, we have talked about this before, but we're reaching a critical point in this mission, which is about to happen probably as we speak.
Indeed. It's actually from now a couple of days away, 10th of April 2020. This spacecraft, which is called Bepicolombo, I can't remember why, but I'll find out in a minute, is to explore Mercury. In fact, it consists of two, actually, which is perhaps why it's got a double-barreled name. One is an orbiter to sort of to observe Mercury and sense the gravitational field. That is the Mercury Planeter Orbiter. And the other one is the Mercury Magnetospheric Orbiter. One is MPO and the other is MMO, so that doesn't account for Bepicolombo. These two spacecraft will eventually wind up in orbit around Mercury, but not in the near future, I have to say. Yeah. Let me just backtrack for 1 minute. Because Bepicolombo, of course, and I did know this, but I'd forgotten, Giuseppe Bepicolombo, who was a scientist at the University of Padua in Italy. And he was the man who proposed the interplanetary gravity assist maneuver. The way we get this gravitational kick, because that is really important to the story of Bepicolombo, and in particular, it's important to what we're celebrating today. I should say that Bepicolombo himself lived from 1920, so he would have been 100 years old this year, but he actually sadly died in 1984. Quite a young man at the time, modern standards. So why are we talking about it? Because on the 10th of April, Bepicolombo, which was actually launched, I think, 18 months ago, will pass the Earth at a distance of about 13,000 kilometers, which is a whisker more than a collision.
Yes, it is. That's mighty close.
Yeah, it's mighty close. And that is all intentional. It's not accidental. It is the first of a number of these gravity assist maneuvers. In other words, the first of a number of gravitational kicks that it will receive from the planets. And as I said, it's the first. Okay, it's doing 9 altogether, Andrew. Wow. 9 of these, yeah. First of all, the Earth, and then there are 2 with the planet Venus, and then 6 with Mercury, with it eventually going into orbit around the planet Mercury.
So hang on a sec. It's going to go to Mercury 6 times before it actually stops and says, this is where I got to be.
Here we are.
Oh, right. Yeah, sorry, didn't recognise you.
Yeah, so it's all about losing energy as the spacecraft, sending a spacecraft to the sun actually takes, if you're going to do it all with rockets, it's a lot of energy because you've basically got to get rid of the orbital energy of the Earth, the fact that the Earth's going around the sun at 30 kilometers per second. You have to lose that to get into the inner solar system, although paradoxically, you're going to a planet which orbits the sun much faster because as you get nearer the sun, in order to stay in orbit, you've got to go faster. So you're losing energy, but effectively gaining speed to catch up with Mercury. But yes, it's as I said, it's an amazing story. That in total, that journey is 8.5 billion kilometers, which would take the spacecraft way beyond the orbit of Arrokoth out there at the edge of the solar system. So it's really extraordinary. And it will do 18 orbits around the sun before it actually goes into its operational orbit around the planet Mercury, which is scheduled for the 5th of December 2025. So we're still quite a way away. Yeah. So a journey like that is not just, Mercury is nearby, we'll just plonk a spacecraft down there.
That's what you'd think, though. I mean, in terms of proximity, it's a much closer planet to us than the gas giants. And you'd think, that's an easy trip. We can just whip over there in a few months. But no. And just because, you could do it, Andrew, but you'd need an enormous rocket to give you the oomph to basically to drop it into the inner solar system and that loss of energy that I spoke about. What's it going to do when it gets there? It will, as I've said, the spacecraft is actually 2 spacecraft, really, not just one, and the 2 components, the planetary orbiter and the magnetospheric orbiter, will essentially give us probably the most comprehensive survey, if you like, of Mercury. The characterization of Mercury's magnetic field, something really important, because Mercury actually has a surprisingly large magnetic field. Everybody thought it would be magnetically dead, but it's not. That was discovered by, I think, the Messenger spacecraft.
the magnetosphere of Mercury, because it's got a magnetic field. It has a magnetosphere, a bit like the Earth does, with which modifies the sun's magnetic field. And also, they're basically the investigators will use the orbiter, the cameras on the orbiter, but also its the gravitational force that it feels to look at the interior structure and the structure on the surface. It's going to be, I think, quite a spectacular mission, and I think 5 years down the track, heaven permitting, we'll all still be going strong. I think you and I might have some interesting conversations about it.
I'm sure we will. And another good thing about this particular mission is we'll get the data reasonably quickly compared to other missions.
Yeah, you do.
Yeah.
You don't have to wait, this 18-month wait as the old dial-up connection takes so long to bring the data back, which is what's happened with New Horizons, of course.
Yes, indeed. And we've used gravity assist before to help slingshot spacecraft to various destinations, and I suppose the great example of that would have been the Voyager missions.
Yes,
because they needed to do that to enable those craft to reach such vast distances, as far as I'm aware.
That's quite right. In fact, pretty well all the missions that, other than ones to the planet Mars, have used this technique. I'm not sure about Galileo. I think that went straight to Jupiter. But New Horizons was slingshotted by Jupiter. Juno actually had a slingshot from the Earth, the one that's in orbit around Jupiter at the moment. And maybe Galileo did the same thing. And then Cassini had, I think, 3 or 4 gravitational slingshots before it got to the planet Saturn.
Okay, so this slingshot happens this week, but it will only be the first of many such slingshots around. It's going to slingshot around 3 planets, ultimately, isn't it?
Indeed, that's right. Yes. So, it's curious that the target planet is one of them.
Yes, it is. It just makes it a bit strange.
Counterintuitive, that's right.
Well, and Mars is Mars. I should say Mercury is a fascinating planet. Just looking at it, when you see some of the photos of it, it's pockmarked. It's got an ultra hot one side facing the sun. They're very, very cold on the other. It's really an interesting place. They're probably going to learn a hell of a lot.
Indeed, that's right. It's not a place to go for a holiday, even when you're not in lockdown.
Well, I'm not allowed to now. So
no,
I'm surprised they're getting away with this.
Yes. Well, they launched it 18 months ago, so October 2018. Too
late.
Yeah.
All right, well, we'll watch with interest, because there'll be more to tell about this story, probably in about 5.5 years, but it'll be worth waiting for. You're listening to Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, I know last week we promised you extra content for our patrons, which we did not deliver. We are blaming time constraints. It's like when you get home on the days where you were actually going out for work. You get home and your wife says, did you get the bread and milk? No, sorry, couldn't do it. Time constraints. So that's why we didn't do the bonus material last week for our patrons, but we'll do it this week. There will be bonus material, and thank you again to all our patrons. And if you would like to become a patron of the Space Nuts podcast, patreon.com/spacenuts, patreon.com/spacenuts. You can support us any way you like, $3 a month, $5 a month, $10 a month, $1 million a month. Got a few that do that. But it's optional.
Well, you're keeping them to yourself.
You don't have to. You do not have to. It's just something that some people decided they'd like to do and contacted us and said, can we do this? And we set it up, and there it is. And we do appreciate your support. Now, let's move along, Fred, to this strange and unusual situation where astronomers have detected the first double helium core white dwarf gravitational wave source. What on earth is that? I mean, I'm very confused.
Well, I'll confuse you more because its name is J2322 plus 0509.
Yeah, okay. Great. That tells me a lot.
Yeah. So, okay, helium core white dwarfs are a sort of species of white dwarf stars. White dwarfs are the end product of stellar evolution for stars of around the mass of the sun. So when the sun runs out of fuel, its core will wind up as a white dwarf star, and it's basically a cinder. It's hot. In fact, they're very hot indeed, but they gradually cool down because essentially nuclear reactions have stopped, although their atmospheres still at some level have nuclear reactions. Now, there is a category of these things which are at the low mass end. If I remember rightly, they're kind of half a solar mass or something like that, which are called helium core white dwarfs, and that comes about because of the remaining nuclear fuel that there is left in this white dwarf. It's still a cinder at the end of its life compared with something like the sun, but it's got stuff happening on it. So these have been predicted, and I think there's another theoretical prediction that suggests that they occur in what we call binaries, in other words, in pairs, one orbiting another. Many, many stars do that. In fact, it may even be as high as 50% of all stars are members of binary systems. It's a lot. It's a high number. It might not be quite that high, but it's something like that. And so there's always been a prediction that you would expect to find these helium core white dwarfs orbiting around one another. And that's why this story has hit the headlines, because now astronomers have found one. And intriguingly, they found it because of its gravitational radiation. So this comes about because of, the detectors that we now talk about, the LIGO in the United States, Virgo in Italy. I'm not sure how many more have come online. I think there is another one online already. I should check that up. But we now have this sort of mini flotilla of gravitational wave observatories, which are routinely scanning the heavens for gravitational waves. And if you've got two very massive objects, something half the mass of the sun, and two of them close together orbiting around one another, then they're going to emit gravitational waves. And that's what's been found. What has intrigued the scientists who've done this work is that you'd expect if you had two stars orbiting around one another, that would become what's called an eclipsing binary. One star passes in front of the other, and so the total light dims because you're only seeing the light of one rather than two. But that doesn't happen in this case, and it's because the plane of the orbit is at right angles to our line of sight. In other words, we're seeing them basically it's projected against the sky. One's orbiting around the other with no eclipses. One doesn't pass it in front of the other one. I'm not
always within our line of sight.
Both always within our line of sight. That's exactly right. So there's no change in brightness. However, there's enough of a tilt that you can actually find a radial velocity, which means a speed towards or away from us. And using actually the what's called the MMT telescope. MMT used to stand for multiple mirror, but then they replaced, I think it had 7 small mirrors, a bit like the Giant Magellan telescope will have, except much smaller. But those were replaced by a single mirror a number of years ago. So I'm not quite sure what MMT stands for now, but it's still called the MMT telescope. It's a bit like the AAO, which is no longer Anglo-Australian Observatory or Australian Astronomical Observatory, but Australian Astronomical Optics. Keep the initials and
just change the name.
Change the name. That's right. Yeah. So so that's been confirmed as a binary, but it's the gravitational waves that are the real perhaps inspiring part of this story, that we're actually finding things that were predicted, but finding them by the fact that they're revealing their gravitational signature as they orbit around one another. It's astonishing stuff. If you and I had talked about this even 4 years ago, people would have said, you're off the planet, you're loopy. But it's really happening. So this apparently most of the gravitational wave detections that we've talked about have been merging objects, merging neutron stars or merging black holes. And that's when the two things are, at the sort of end of this dance around each other, and they coalesce and become a single object. Well, this is also going to happen to the white dwarf pair as well, but not next week or the week after. 6 or 7 million years they're talking about the merger between these two objects to form a single, more massive white dwarf star.
I guess we'll just have to wait till then and talk about it when it happens.
Yeah, we might. Well, we might be in another place by then. But yes, why not? Let's put it in our diaries. Yeah. 6 or 7 million years.
I suppose the thing about gravitational waves, and we often, after we talk about them, get questions from people, but how difficult is it to tell the difference between various gravitational waves? And they're all caused by different things.
Yes.
So how do you know which is which?
Yeah, and that's the clever bit of all this, because there's, gravitational waves have got a very specific signature depending on the masses of the object, their separation, and other physical parameters. It can be modelled very accurately. You're right that there will be some uncertainty, but you and I have seen the traces of these gravitational waves, and you can see the structure in them. You can see how they change over time, particularly the ones with black holes merging. The gravitational waves, when you look at the period and the amplitude of the waves and the structure within them, you can basically tell what it is you're looking at, which is extraordinary. But it's not like looking through a telescope. Oh, yes, that's a star, that's a planet. There's a lot of computation involved. But the astrophysicists who do this work are pretty confident in what they're seeing. And it all is self-consistent as well. The observations seem to be telling all the same story.
Yes, all right. Very interesting. And you've got to wonder what else is out there that could cause gravitational waves that we haven't discovered yet.
Yeah, especially as gravitational wave detectors get more sensitive. And one of the comments that's been made, and I should have said that one of the co-authors, I think, are in the United States. Yes, CFA, which is the Harvard-Smithsonian Center for Astrophysics, and the University of Oklahoma, there's a co-author from there. So one of the things that has been highlighted is that this is the kind of source that the LISA orbiting gravitational wave observatory will be able to detect and will actually be able to, to analyze perhaps in more detail. So that these astrophysicists are saying that the star will be used for verification on the Laser Interferometer Space Antenna, that's the LISA, which is planned for launch in 2034. Wow. That is forward-thinking.
It is rather, isn't it?
It's a very ambitious project. You might remember there was, I think it's about 4 years ago, there was a pilot version of LISA launched by the European Space Agency, just one component of it, just to demonstrate that it will work. And they came, they had results which were really stunning, absolutely above expectations. So the prospects for LISA itself seem really good.
Okay. Let's keep an eye on this, and we will certainly let you know when the next major gravitational wave is detected. Might be a new source too, which will be even more exciting. You're listening to Space Nuts with Andrew Dunkley and the great Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, before we get back to Fred and start talking about answering some of the questions that have come in from our audience, I'm going to introduce you to somebody, Marnie Ogg. Now, Marnie is someone I've known for a little while and is heavily involved in astronomy with Fred. But there's a new podcast, or a relatively new podcast, that's been introduced to our stable called Dark Sky Conversations, hosted by Marnie. Hi, Marnie.
Hi, Andrew. How are you?
I'm well. You're not totally unknown to the Space Nuts audience because we've mentioned...
I'm Mandu's mother.
Yes, that's right. And we've mentioned you many, many times. Now, tell us about Dark Sky Conversations. Fred and I have talked about the Dark Skies project a few times and how it's important to try and maintain the capacity for astronomers to do their jobs without polluting the sky with light. And it's sort of reached that point where it's becoming a more and more serious issue.
That's right. So the idea came to me to talk to people who are interested in light, and not just from an astronomical perspective, but ways that they may use it for their career or ways that they see that it is affecting the environment. So one of the things that we talk about quite a lot is the ecological impacts of light on our environment. So whilst people like Fred have spent a lot of their years campaigning so that we don't have upward wasted light that's destroying the night sky and we can't see the stars so well when we do that, there's now a new understanding that whilst we're getting very good at shielding our lights and putting the light down to the road or down to the surface that we need to light, what we've actually done is put the problem from up in the sky down onto the ground. And particularly with ecology, you've got pollinators that are now not pollinating at night because they're attracted to the light. Yeah. You've got nocturnal animals that can't go to sleep. You've got predators that are actually coming in and preying on nocturnal species because they can see it, etc. So we're completely changing our nighttime environment, and it's those sorts of people that I'm talking to. So yeah,
okay, that's fascinating. I mean, I know where I live in Dubbo in central New South Wales. They have actually worked really hard to cap all the lighting so that it's pointing down. We don't send as much light upwards as we used to, and we use a duller light. We if you drove into our town or flew over it, you'd notice that it would have a more of a red hue kind of look than the bright white light that we're used to of the past. But that's only part of the story by the sound of it.
It's only part of the story, and really the other thing that I've just finished a podcast with a gentleman called Professor Sean Kane, who's based in Victoria, and his work is very, very much involved with human health and the impacts of light. So we know how badly we feel if we've got the moon shining in through our bedroom, full moon shining in it.
Oh yeah,
we're disrupted. Yeah,
I'm useless when that happens, and there's a couple of times of the year because our house faces just 2 degrees off absolute east.
Okay,
and so there's a couple of times of the year where the sun is in, or the moon for that matter, is in such a place where it just gets through a little crack and hits me fair in the face.
Yeah, and it's as annoying as hell, isn't it?
It is horrible. and I did read a report once about the effects of light on humans, and it is the biggest killer when it comes to sleep, or probably the second biggest. The other sleep killer is co-sleeping. We actually shouldn't be sleeping in the same bed as someone else because it actually is detrimental to our capacity to sleep properly.
Haven't heard that one.
I did a study on it. Believe me, it's true. My wife keeps reminding me. But light is the big killer.
Yeah, well, that's what Sean's study does. And so he's actually looked at not only the fact that there's a correlation between sleep disruption, but that if you, for example, put people in an overlit environment for as little as 3 weeks, you can actually take people from being completely healthy to pre-diabetic just because their sleeping patterns are being disrupted by artificial light at night.
That's amazing.
So we're just about to put that one up online. So he's the sort of calibre of guest that we've got on.
Fantastic. It sounds great. Well, if you want to catch up with Marnie and her guests, it's called Dark Sky Conversations. You'll find it on your favourite podcast distributor. Thanks, Marnie.
Thank you very much, Andrew.
Space Nuts.
Now, Fred, we better get stuck into these questions, and we've got a couple to knock over today. And the first one comes from Pat. Pat says, hi, Pat, by the way, thanks for your question. I have a quick question for you, which comes in 27 parts. Now, this morning, 31st of March, I'm assuming, because there's no 31st of April, Pat, as much as I'd like it to be. But on my birthday as it turns out, Pat. You were headed to work at about 5 a.m. He says he looked to the sky, as he always does, and observed a long line of what he assumed were satellites moving across the sky. Now, what was interesting was the line of satellites kept coming for just over a minute. He says, I am in Brisbane, and I was looking to the east. The satellites appeared to be coming from the region of the Southern Cross to the south. They passed just below the apparent cluster of Saturn, Jupiter and Mars and vanished to the north-northeast. They were spaced about 4 finger widths apart. That's an official unit of measure. But the gap got closer and closer, and just before the long line of them ended, I saw 3 closer together, with one of them below forming a triangle. The one below slowly overtook the last 2. It was as if there had been a launch and the constellation of satellites was spreading out to their set orbits. What group of satellites would they have been? SpaceX? I think the other company's Blue Horizons, isn't it, Fred?
It's OneWeb, the other company that are doing constellations, and they've certainly launched. But I think these would have been the SpaceX constellation. It's called Constellation 5, I think, but it is actually the 6th lot of Starlink satellites. They were launched on the 18th of March. So they are still, I actually followed up on the Heavens Above website, which is where you can find an interactive dynamical display of these Starlink satellites. And I followed that up by coincidence the day before the report, or assuming it was the 31st of March, the day before Pat made his observation. And they're still in a close line with exactly as Pat says, 1 or 2 that are, sort of going into slightly different orbits, which is why you get this triangle effect with one looking as though it overtakes the last 2. So I think it's pretty clear cut. I think that was, what's it called? Launch 5, I think, of the Starlink satellites. It's actually the 6th lot, but it's called the 5th launch. Okay. That's because there was a 0th launch at the beginning.
I've seen some spectacular photos of people who've observed these.
Yes, that's right.
You just see these row of bright dots in the sky. It looks really impressive.
Yeah, it does look impressive, and of course it's not exactly cheering astronomers up.
I was about to say that. Yeah.
Potential interference with observations, although SpaceX have been certainly working with astronomers to look at mitigation possibilities. This particular project will eventually have 12,000 satellites in orbit. At the moment, I think they launch 60 at a time, so it's of the order of 300, something like that are there. Just to tie up a loose end there, Heavens Above is a great website for exactly what it suggests. It started off being a product of the German Space Agency. You can find it at heavens-above.com. And on it, there is this dynamical display for whatever is the most recent tranche of Starlink satellites. And at the date that Pat was looking, it was the 6th tranche. So you can have a look at that. It's really worth just checking out. It's a very, very effective display.
Okay, the Heavens Above website. And these satellites, correct me if I'm wrong, are simply being designed to provide internet services. Is that right?
Yeah, that's right. It's global internet.
Yeah. Okay, that could change the game, couldn't it? Interesting.
It will do. There's no doubt about it. That's right.
All right. Thank you, Pat, for your question. Let's move on to a question from Peter Haig. Hi, Andrew and Fred. On the 193rd episode of your show, to which I have listened, Professor Fred mentioned that the Roche limit for the moon would be a bit over 9,000 kilometres. Is it correct that if any part of the moon came within this distance, that part of the moon would begin to break up? Regolith would float off the surface and begin to form a ring, but bound material would come closer until Earth's gravity became or overcame the binding force. Love the show. Keep it up. Thanks, Peter. I suppose that would be an interesting phenomenon if the moon just sort of crept into that Roche limit. rather than collide with us, for example, would we see bits of it break away and start sort of creating a ring around the planet?
Exactly. That's exactly what happens. But it's a little bit more complicated than that. And I might just mention that figure that I gave for the Roche limit of 9,000 kilometers for the moon, I think that's center to center as well. So it's quite close. But that's assuming the moon is rigid, because you get a different answer if it's fluid. It doubles effectively if you've got a fluid object which is approaching the Earth. Really, in many ways, that's, it's really just a nuance on the issue. But what I would recommend here for Peter to do is have a look at the Wikipedia page on the Roche limit. That's what it's on, just Roche limit. And there is a lovely set of diagrams right at the top of the page, which shows exactly what happens when something like the moon approaches something like the Earth. And you can see that it's a long way away. It's a sphere. The moon is spherical. But when it gets near, it gets highly elongated. It's being deformed by the tidal forces. But then when it hits the Roche limit, basically, it would be the whole moon that would start to disintegrate, just because the tidal forces are so strong. It's a bit like when you think of the tidal bulge in the Earth's oceans that are caused by the moon. Yeah. That bulge, of course, is elongated in both directions, both towards the moon and away from it, which always seems counterintuitive. But what you're doing is you're just putting a gravitational pull that's trying to turn the Earth into an egg shape. That is exactly what happens with something getting too near getting near the Roche limit. Eventually, the egg shape just can't hold up. It wouldn't just be stuff coming off the leading edge. Basically, the moon would start disintegrating as it crossed the Roche limit. And the debris, exactly as Peter has suggested, would form a ring around the Earth.
But we probably wouldn't be around long enough to
no, I think that will be something quite spectacular, yes.
Yeah, right.
And of course, the moon is actually going the other way, as we all know.
It's slipping away from us.
Yep.
But not in a hurry. Definitely not in a hurry. Thank you, Peter. Hope we answered your question. Thanks for sending it in to us. And I also want to send out a thank you, Fred, to all the people who listen on their various podcast platforms who have provided reviews. This was made aware to me by Hugh, who said that all of the reviews are glowingly positive, and we really appreciate that. Thank you so much for doing those reviews. I was unaware, to be honest, that the reviews were done. I don't really get the opportunity to go from podcast platform to podcast platform and check all that stuff out. But it's great that you feel obliged to do that for us. So thank you. Yeah, very, very good reviews. What else did I
was unaware of that until this minute, Andrew.
Yes, there you are.
So thank you for telling me.
And also thanks to our social media supporters on Facebook and YouTube, and apparently we are on Twitter and we are on Instagram. So you can find us just about anywhere. And the podcast group, the Facebook Space Nuts podcast group on Facebook, is a place where you can all get together and mingle and talk to each other about various things, ask each other questions, talk about your telescopes, mine's bigger than yours, that kind of thing. I think it's great that the Space Nuts community is getting together and talking to each other. I really, and occasionally I'll chime in. And I solved the mystery of the spelling error on the book cover that they were discussing.
Ah, did you?
Because the picture was so small I couldn't see what they were talking about. I had a closer look. I'd accidentally uploaded the draft cover, and I remember my brother saying, "No, I'll send it to you again. There's a typo," because he'd typed. Hang on a sec. I'm just going to grab it. Why do I put it so far away? He typed annihilational instead of annihilation. But I've got the one that's right. So I didn't see the problem, but now I've figured it out. So, the problem doesn't exist. It was just a mistake on my part uploading the wrong cover picture. So that's been resolved. Something else is happening tonight, my time, which by the time everyone hears this will have happened. But I'm going to go on Throne tonight and do a little Q&A with the Space Nuts audience about the book or whatever they want to talk about. So that'll be a lot of fun. So I'm looking forward to that. Thank you, Fred, as always. That'll be it for this week. We'll catch up with you again on the next edition.
I hope so, Andrew, and stay well and look after yourself and keep up the good work. Speak soon.
You too, sir. You too. Professor Fred Watson, astronomer at large, makes one half of the Space Nuts team. Actually, it's not half because there are thousands of us now, so let's just say we make up a minuscule portion of the Space Nuts fraternity. But we will be back again next week with another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.